Okay. Same thing holds true with triple integrals as double integrals, is you want the innermost limits to usually be the most complicated and the outermost limits to be the simplest here. Now, on this example, free everything was given to us, and the point of this problem is to show that sometimes switching the order of integration helps and makes it a little easier. If we think about inner limits being simple, outer limits being complicated, it doesn't really apply here because 1 and 3 are very simple, and that's okay. That doesn't really change things for us too much. But when we're setting it up ourselves, we need to make sure we're reducing the number of variables as we move out. And then just be careful working through this. Since we have more variables, it's easy to confuse which one's actually a variable and which one's kind of constant at that time, but that just takes some practice in working through them. So yesterday we worked through the first integral from 1 to 3, and we got to this point here, and the reason that we got stuck is because that second to last step that was there is pretty much not impossible, but very difficult to integrate as is there. So we switched the order of integration, which means we had to switch our limits of integration around, not just reverse them, but rewrite them. And so now we have this new integral. It's a much simpler integral to go through and solve here. So let's work through setting up or solving this one. So the outer integral still is going to be the same. We're now integrating 2 sine of y squared with respect to x. So that whole thing, 2 sine of y squared, is just a constant. So all that times x. And then we're going to evaluate it from 0 to y. And yeah, I'm not going to show the middle step here, but hopefully you can recognize if you plug in a y and then plug in a 0, 0 is going to make the whole thing cancel out here. So what we're going to have is from 0 to pi over 2, square root of pi over 2, 2y sine of y squared. And that's doable now because we can just use u substitution. If we let u equal the angle for our trig function, so y squared, then du is 2y dy. And you can shift around constants, but if you recognize 2y is what we have out front here, we don't have to add another constant to that. If you want to go back and find the limits of integration, that is a-okay, but I'm just going to back substitute. So if I write it in terms of u, we still have y equals 0 and y equals square root of pi over 2. Now this whole integral is just going to be sine of u, which is easy. So antiderivative of sine is going to be negative cosine. We're going to back substitute, so instead of u, we have y squared, and then evaluate that from our limit to our limit. A little bit of substitution, we get negative cosine of square root of pi over 2 squared, so just pi over 2, minus a negative, so plus cosine of 0. What is cosine of pi over 2?
0 pi over 2 squared is just power.
So we had the square root of pi over 2 squared. Yeah. But yes, cosine of pi over 2 is 0, and cosine of 0 is 1. So we are just left with 1. And it's almost kind of frustrating to work through a whole problem, just get 1 as an answer. But that's it. Kind of almost appreciate the messier answers when you're doing things like this sometimes. So the point on that one is just another technique for solving these is switching order of integration can definitely help there. And there's nothing initially about the setup of this problem that kind of flags us and says, hey, let's switch this to a dz, dx, dy problem. But as we work through it, it's just another technique we use. Okay? Next 3 examples just have us go through and set it up. We're not going to go through and solve these. We're just setting up the integral. Again, that's kind of the important piece of this section or chapter. Now, granted, as we work through any one of these, it may be handy to kind of convert to a coordinate system or change order of integration, but we're not going to worry about that. We are just going to go back and set up the following guys. So set up triple integral for the volume of the described region, do not solve. The region in the first octant bounded above by that cylinder and between those planes. I do not think I have these graphed ahead of time, but I'm going to graph them. Z equals 1 minus y. And if you recall, we worked with cylindrical surfaces. Hopefully it kind of makes sense why this first function is a cylindrical surface. Remember, in 3D, if you're missing one of the variables, like we're missing x here, that means we know we kind of stretched it along that x-axis. And their default, there we go. So now it's kind of pointing in the same direction there. So we have just that parabola stretched along the x-axis. That's our first surface, where we're bounded above by, and between the vertical planes x plus 1, x plus y equals 1, I mean, and x plus y equals 3. Okay, so that's kind of a lot to look at right there, but do this in the catch up so I can spin it. we essentially have two parallel planes to each other given by these kind of like seafoam greenish lines. Sorry, it's not letting me spin it now. It's been kind of slow. There we go. Okay, so what I want to do is look at this guy from top down. So lines are a little hard to see, but these parallel lines that have that negative slope, those are coming from our planes. And the dark shaded part up here, we actually don't care about. That's below the axis. So this reddish parallelogram in the middle is the region of integration we're working with. And then the top of that surface is given by that paraboloid. So hopefully, or not paraboloid, that cylinder. So hopefully it kind of makes sense the shape we're working with here. It's kind of like those barn-shaped pieces, but cut at a diagonal. Even if we don't look at the graph, hopefully we can still figure out how to go through and set this up. When we are finding volume with triple integrals, I'm going to leave space for my limits. The integrand is always going to be 1. Okay, if we're using triple integrals to find volume, integrand is always 1. And let's stick with the default dz, dy, dx and see if that's good enough. If not, we'll switch it. But that may be sufficient for this here. So inner limits for z. What are our limits for z going to be?
The plane to the curve.
Rightio. And so our plane on the bottom is just z equals 0. So we're going to have a 0 down here. And then our curve on top is z equals 1 minus y squared. So 1 minus y squared is going to be the top function. It's very similar to this top function minus bottom function, only instead of making them the integrand, they're going to be our limits of integration. But we're looking for the same parts here. And also remember, you can think about these limits as always being like z equals something, z equals something. If those make you the right shape, then you're probably on the right track there. So you can go back and check a little bit with some graphing utilities. Okay, so bottom to top, how about y? What is y going to range from? And for this, it may be handy to think about that region of integration, which that graph's not cooperating, so I'm going to sketch it over here. So the region that we are integrating over was that little parallelogram shaped piece. So we had a diagonal line, another diagonal line, and then it ended up looking something like this here. And if I go back to that graph, it would make more sense here. But if we think about this, I can explain another way to get this too. But if you recall from that graph, it kind of looks like this thing here. Okay. Some of these are relatively easy to get the equations of. If we think about x plus y equals 1, we can easily solve that for y. And so if we went back and solved that for y, we get the equation y equals 1 minus x. Similar for the second one, that would result in y equals 3 minus x. And that's kind of responsible for these lines. I hope that's easy to see here. As far as for our surface, what we really care about is where this cylindrical surface intersects the xy plane. So if we go back and let z equal 0, that's another way we can kind of see what shape this makes here. So we would have 0 equals 1 minus y squared, or y squared equals 1. That's not what I'm going to do. Oh no, that's good. Yeah, it is, because then that means y equals either positive 1 or negative 1. Since we know we're in the first octant, we know we just have y equals 1. And so that's what's responsible for this line right here.
So we want to change order of integration.
We can switch the order of integration around.
I assume, oh wait,
And why would you suggest that?
because y is similar to x.
So let's do that. Okay, if we were to keep this as dy dx, right now we have to split it in a bunch of sections here. So since we have a horizontally simple region here, Russell suggests doing this as dx dy at the end. And yeah, I think that definitely would make this easier to set up. So we'll go with that. Okay. So go ahead.
So how can you just look at it and say and know that you want to switch it?
Russell, how can you just look at it and say you know you want to switch it?
Because the x, we're going to have to deal with functions.
Can you hear him, Cole?
Yeah.
And the y is just straight constants for there.
Okay.
So yeah, the lower limit on this shape here is just always going to be y equals 0. And the upper limit is always y equals 1, so they're constants like he said. But in your x direction, that's where you have that angle happening. So it's like a horizontally simple region. And if you think back to when we said horizontally simple, we said that would be a good case to do a dx dy situation here.
All right.
If we kept it dy dx, and I'm not going to write this all out there, but if you kept it as dy dx for this little parallelogram, we'd have to go through and split this up into a region over here, and a region over here, and a region over there, because your y is always changing which one's on top. It's not always the same function on top and bottom. So it's doable that way, but Russell's suggestion is going to make it easier. That is also going to change this, though. Instead of having these things solve for y, I'm going to change them to solve for x. So that's going to be x equals 3 minus y. And this one's going to be x equals 1 minus y. And with those changes, hopefully it makes it easier to see what limits of integration are. So for our middle integral, for x, what are going to be limits of integration?
1 minus y and 3 minus y.
And so it's going to be from the upper or larger one, which is 3 minus y, to the lower function, which is 1 minus y. And finally, limits for y?
0, 1.
Not yet. And this one wouldn't be too difficult to go through and solve. So if you want practice, go for it. I can check the answers and give them to you. But just to set up here, what we're going to go through.
Is this 4?
Huh?
Is that 1?
No, we'll get to it in the next section.
Okay.
Yeah, it's on page 31.
Okay, I didn't know. I was gonna-
Nope, nope. That one we're good. Okay, questions? All right, well, if you do, let me know. Example 5. Set up the following triple integral to find the volume described by the region. Do not solve the upper hemisphere of this. And this one, I don't think we'll need technology to graph. We can kind of imagine what a hemisphere is going to be. If we consider just the top half of a sphere, okay, right now our sphere has a radius of 1. I can tell that from this little value right here. And so there's kind of a rough sketch of the shape we are working with. Okay, and since we're just the top half, we have the positive square root until we're at the bottom of it. Now, an easy way to find this volume is just to use the equation for volume of a sphere and divide it by 2. Okay, so if you really want to know the volume of this shape, this is not the best way to go through and do it. But again, the practice here is just how do we set up these triple integrals based on the regions we're working with. So, like last time, if we're talking about volume, the integrand is still just going to be 1. If we still just try that default dz, dy, dx, at least gives us something to start thinking about here, and then we can change it if needed. Okay. So for z, what's going to be our limits of integration for z? What's the bottom of this surface?
0.
Yeah, the bottom of this surface is just that xy plane. If we're talking about the top half, we're just talking about the bottom. Okay, and then that function is going to be our upper limit. Because if we think about going in this solid and traveling up and down, the bottom is bounded by 0, and the top is always bound by this hemisphere, so it's going to change. Limits of integration for y. How are we going to find those?
It's a circle.
In this circle, what I would say to do from here is think about the region of integration that this thing sits over. So if you really look at this shape from the top down, what shape does it make here? And we do have a circle in this case. If we think about that hemisphere, we're cutting that in half. So we're talking about this circle right there. And the equation for a circle, we know, so we can just use that. Or again, if we didn't do it that way, we can still go back to this equation, let z equal 0, and then go through and solve that. We're going to same equation there. We're just saying when does this surface intersect the xy plane? So whether you know a circle or that's good.
So if we were going to do this, and you see it's a circle, could you do the first step and then convert to polar?
Mm-hmm.
Like just halfway through?
You can convert from the beginning, you can convert halfway through, that's fine. Yeah.
Okay.
Because really, once you go through and solve the middle, we're basically back to double integral case we talked about before. So we know how to go back and work with those, and it's fine to convert the polar coordinates. There's nothing wrong with doing the middle of the step there. Each one's kind of like its own little piece there. So yeah, that would be okay. But since we're just setting it up, we'll go ahead and leave it in rectangular coordinates for now. For y, our limits of integration are going to go from the bottom of this circle to the top of this circle. And so if we get this equation to have y by itself, we end up with this. So we're going to have the negative square root of 1 minus x squared in the lower limit and the positive square in the upper limit. Which hopefully, like Russell said, we recognize polar coordinates would be helpful here. Okay. And they definitely would. If we had to go through and solve this, I would definitely convert the polar coordinates. All right, last one, limits for x.
1 negative.
There we go.
1 negative.
Yeah. Okay, the whole entire circle here. We're not splitting off into these sections, from the whole circle, so from -1 to 1. Okay. 4.7 is all about converting triple integrals to other coordinate systems. So I won't worry about converting this now, but there's really nothing too tricky about this one. We know that x squared minus y squared is r squared. So we can go back and do those conversions, do in terms of theta and r, and that'll be fine. But we'll wait and do it officially in the next section. I'll note on the side. Note polar coordinates would be handy. And actually, technically, it wouldn't be polar coordinates. Or polar coordinates are technically two-dimensional. Now they're working with this three-dimensional piece here. We have z's as our problem too. We're working if we use cylindrical coordinates, but we'll get to that later. Okay. All right, one more example on this page. Set up the function cylindrical, again, to find the volume. Do not solve. Region bounded by z equals x squared plus y squared below, and then that other function above. What does x squared plus y squared plus z squared equals 6 look like? Even nicer than that, even simpler than that. Yeah, it's just going to be a sphere with a radius of square root of 6, which is kind of weird, but oops. So we have just a sphere, and that's what's bounding this guy on the above. That's going to be the top part of this. And if we graph the second equation they give us, so z equals x squared plus y squared, that's going to give us this parabola. So we're looking at this piece where they intersect here. And I don't know how to cut this off to look at just portions, so use your imagination. But we're talking about that inside section, that kind of paraboloid cup-shaped piece with a rounded top. So hopefully that makes a little bit of sense what we're working with there. Okay. If we think about where these two intersect, what shape does it make? And so when we're setting up our region of integration, we're going to have to say, okay, on the xy plane, this paraboloid is just a point, and this sphere makes a giant circle. But neither of those are really what we care about. What we're going to care about is where do these two things intersect. So this circle up here is what we're going to want to think about projecting onto the xy plane. Again, it's not like this. So the setup for this one's going to be a little different. We haven't really talked about a lot of problems like this where we're looking for the intersection of shapes. We'll have to worry about that. Let's just get it started like we did before. I won't bother trying to sketch this one. Let's just jump into the equation. So we have our three parts. We talk about triple integrals. Integrand is still 1. Just still stick with that default and see if that's good enough. And honestly, it starts off not too bad here. What are the limits for z going to be? Think about the shape we're working here. What's the top part of this shape controlled by? The sphere or the paraboloid? Yeah, if we're talking about this like piece, I can't really point to it, but like inside the sphere, we have that little paraboloid piece with the curved top. That's the only section we actually care about here. So the top of this solid is coming from the sphere, and the bottom of the solid is coming from the paraboloid, right? Does that kind of make sense? Got a nod here, not much other places. So let's hope it's just delayed. So the top portion of this is coming from the sphere, and I'm just going to write that in there for now. I'll put the equation in just a second. And the bottom half of this is coming from the paraboloid. So we need to say, okay, well, I need those equations for z equals something and z equals something here. Paraboloid is done for us. It's just z equals x squared plus y squared. But we are going to need to go through and solve the sphere. And like Russell said, we are going to end up using the positive square root. That is true. So if I get z by itself, you got this. And I'll leave that there. I'll rewrite it. You guys can write however you like in your notes. But we're going to have x squared plus y squared as our lower limit, and just the positive square root for our upper limit. So it is originally the top portion of this solid, and then the bottom portion of this solid. Limits of integration for y and z, y and x, so those are going to be a little more complicated. And again, to find your limits of integration for y and x, go back and consider that region that we're working with here. So like we said, we know it's going to be a circle. I mean, we can look at these two shapes and tell they intersect in a circle, but we need to know is what's the equation for that circle. We need to know, well, what is the radius of that circle where these two guys intersect. I don't know why. Okay, so not this dark red part, that's a paraboloid we don't care about, but this kind of like muted red color in the middle, that's a circle we're going through and working with. And we can zoom in and just kind of approximate this, and that's one way to do it, but that's not good enough. We need a better way to go through and do this. So we need to figure out, is this circle is the intersection of the two curves. How do you find out where two things are equal to each other or where two things intersect?
Instead of equal to each other.
Instead of making to each other, we're essentially just going to work through and solve like a system of equations here. So our first equation is z equals x squared plus y squared. Our second equation as written is x squared plus y squared plus z squared equals 6. And we could go through and set them equal to each other, but I'll show you a faster way to go through and solve this one, and you may see it here too. We right now know that x squared plus y squared equals z. And then our second equation, we have x squared plus y squared. So let's just plug that in. Let's just write z instead of x squared plus y squared. And that will save us a lot of time in trying to go through and solve this. So if we do that substitution here, we're now going to have z plus z squared equals 6. And it might not look like it's easy, but that's pretty easy to solve. My favorite way to solve quadratics is to factor. So we'll do that. Hopefully that looks familiar. Which means our two solutions are x equals -3 and x equals +2. Okay. So took on two curves. Sorry, z equals, yep, that should not be x. That should be z. Thank you. Okay. Which one are our curves actually intersecting at? Is it -3 or is it +2? Yeah, we know that we're just talking about the top half of this shape here. I mean, there's no intersection of these guys. And I don't know why it doesn't respond so quickly. There's no intersection of these guys down below the x-axis. We're talking about above the x-axis. So z equals 2 is the plane where these intersect at, which still isn't the information we need, but it gets us closer. So we know that that's not where it's happening at. We know these two guys are intersecting when z equals 2. So really now we're going to go back and find the trace. And you can pick either one of the curves. It doesn't matter which one you're going to do. They're the same thing at each point. To find the trace when z equals 2. And so if we go back, and let's just take the first one since it's shorter. Okay. If we go back and let z equal 2, that was supposed to be like a 2 in this case. That is it. That's going to be the equation of our circle. Okay, we know we have a circle, and we recognize x squared plus y squared equals number is going to be the equation for a circle. And specifically, we're saying we know we have to have z equal 2 there. If you went back and solved it in the second equation, you'd eventually get the same thing, just a little more math to get there. Let z equal 2 and square it, subtract it from both sides, and the same thing. But this is going to be the equation of the circle that these two things intersect on. And basically, we're going to say, okay, well, that is going to decide my limits of integration. If I push that down onto the xy plane to kind of see how it matches up there, then we can go through and follow all the same things we usually do. So that's a radius of square root of 2. Which means if I do my limits of integration for y, we can get this equation down y by itself. So positive or negative square root of 2 minus x squared. So lower limit is going to be the negative square root. And upper limit is a positive square root. What are limits of integration for x? Last part of this.
0 to 2 pi.
Not 0 to 2 pi. If we were doing theta, that would be okay. But we're talking about x now. We want to know what do the x values range from. So basically, we're saying from here to here.
-1 to 1.
You got the right idea. But the radius in this case is square root of 2. So negative square root of 2 to positive square root of 2. But you're right. It is radius to radius. That part is correct there. Okay. Luckily, we're not going to solve this. This is a very messy looking integral. Another one with polar coordinates would definitely be simpler. But we haven't really done a lot where the curves intersect. And so that piece of going through and finding that intersection is definitely something we haven't done before. So if you have questions about it, feel free to ask, whether it's an email or right now. Okay, but we need to say, okay, well, where do these two things intersect? Set them equal to each other, go through and solve that system. And then once you know where they intersect, we can go back and say, okay, well, what shape would that make on the xy plane? Just kind of carry it down. Okay. Questions? One more little piece here, and we just set this up and I'll give you the answers. We're not going to work through this one too. It'll be a little easier to set up. Another use of working with triple integrals is to be able to do something like we see here. We can go back and find mass of solids of varying density, kind of like we talked about before. The difference between when we did this before and we're doing it now, before we were still talking about just a plane that had varying density. Now we're allowed to be a whole solid that has varying density. And so if we have this solid that's got densities that change, we're going to set up the integral very similar to the way we did before. And I've presented this a little bit differently. Down here is just the mass, it's like that first question that Edwin asked about the homework. This would be the three-dimensional or the three-integral version of that. But anyway, just put it all together here. So you can see, similar idea. If we're finding x bar, we're still going to include x in our integrand. We still need a function for the density of this whole entire solid now. And then it follows a really similar structure for this. And I didn't put in any of the formulas for moments of inertia because there could be a ton of them. But if you're curious, go ahead to your book. If they're not in the notes, I'm not going to require you guys to know them, so you don't have to go back and write them down on your note cards or anything like that. But you can go back and see that there's a whole bunch of formulas that talk about inertia there. Anyway, centroid. We've got some solid, varying density in different places. We want to know where the center is. We can go back and set up these three triple integrals, which have a very similar structure to what I talked about before. Let's do it for one problem here. Find the center of mass of a cube with each dimension equaling 1, given that the density at a point is proportional to the square distance from the origin. And one more extra piece I should have given here. We're going to fix one corner at the origin. It's not a necessary step, but it just makes the setup a little bit nicer here. So if you consider the shape that we're talking about, we just have a little cube. That didn't draw very well. Okay, we just have a little cube sitting there at the origin is really all we're working with. It tells us the density is proportional to the distance from the origin. So the further away we get from the origin, the more dense this piece gets here. So that tip that is the furthest away from the origin is the most dense, and then towards the origin is the least dense. Let's write that as an equation. Put the k in there because we're going to have that. Anytime we're talking about proportional and we aren't given a function, we have to have k. K times what? How are we going to represent the distance from the origin as an equation?
0, 0, 0.
Yeah, so the origin is 0, 0, 0. And then to just some other point, right? We don't know exactly what it is. We're allowing it to be everything. Do you know how to find the distance between points in 3D?
Yeah, the square root of x minus x1 squared plus y.
Yep, and then the lucky thing is, since the origin is 0, 0, 0, x1 minus 0 is just x. So we can simplify this to just x squared plus y squared plus z squared. Okay, go through the distance from that. Now we could work the problem this way, but there's one, not really trick, we'll call it a technique, doesn't sound as mean. There's a technique we can use that showed up in the homework before that definitely helps out a lot. We're going to have to integrate this thing times x or times y or times z, depending on the mode we're talking about. Integrating a square root can be kind of messy. It's not going to be difficult if the little variable up front matches up, but in almost every other case, it's going to be kind of messy here. Another way we can think about writing this is we don't know what this k proportionality constant is, so we can account for a lot of different things here. If we go through and square this whole thing, we're still going to get an accurate representation that's talking about the distance we are from the origin there. So I'm still just going to call it k, but instead of having that square root on there, now we just have a polynomial, and that's much easier to go through and integrate. So the idea is that still a representation of the distance we are from the origin. The further we are from the origin, the stronger all these values are going to get. There's how we found the distance. When we go through and square it, if we have enough information to solve for k, we can make that account for the fact that we squared it, but we're not going to solve for k, so we're just going to do it like this. Again, hopefully that's familiar. The homework's done that a few times there too. It's not something we're going to do a whole lot, but it definitely makes it a little easier to solve by hand. Either way, we need to go back and find an equation for mass, an equation for an x-axis, the y, and the z. Yeah.
But don't your k be squared? Doesn't the k become squared too?
You could, but k is just some constant. It's like when you're doing things with like your constant of integration. If you have two constants, you're adding them together, we usually just call it some other constant. Same idea there. It's a-okay that we still just write it as k. If you want to call this like k sub 1 and this k sub 2, you can. But the idea is it's just some number that's going to count for the proportionality of this, and we don't really care too much about it, honestly. So, yes, technically it is squared, but it's just still a constant, so we'll just do this k.
All right.
All right, we're going to set these up. I'm just going to give you the answer. We're not going to go through and do all the math. I want to be able to talk about the next section a little bit. So, mass of total system is just find that denominator is what we're going for. So we really set up the triple integral for this. So triple integral, and our limits of integration are very simple in this one, so you won't need a lot of room to write them down. If we follow that structure up above, we are going to have the density function that we came up with. And we'll just stick with dz, dy, dx. They're fairly easy integrals to set up, as long as you have that density function here. What are limits of integration for z? This little cube.
So 0 to the top.
Yep, 0 to the top. The top of the cube is just a plane, right? When z equals 1, so just 0 to 1. There's no curve we have to account for here. We have this whole bunch of straight lines all over the place. Okay? It means the limits of integration for y are also 0 to 1, and for x are also 0 to 1 here. If our cube was not at the origin, this would not be the case. So like if we had a cube that was like centered at the origin, we'd have to go back and adjust all these and go back and adjust our formula and change some things there. But that just makes it a little easier. We're not going to work through and do that, but you guys could work through now. It's a polynomial. It's a much simpler process to go through and do by hand there. However, point of this problem here is to go through and set it up. If you were to work through this, eventually we just get k. For the moment about the x-axis, or sorry, we don't have an x-axis, about planes. I wrote this wrong. About the xy plane, about the yz plane, and the xz plane. I'm sorry. I said those wrong there. We're now talking about distance. We are from a plane instead of from an axis there. All right, so a moment about the xy is going to help us to find our z bar. But what this is going to be is we're going to have the same limits of integration. We're still going to have to go through and include that proportionality constant, but since we are talking about the distance from the xy plane, that's what z controls. So we're going to have z times all that stuff we had in the previous one. And you can go back up and look at the formulas up above and kind of see where that comes from too. But again, talking about the distance from the xy plane, that's what z talks about. So z times the density. The answer for this is eventually 7 over k times 12. Yeah, that's not perfect, but all the other ones end up being the same thing. So the setup for the rest of these guys is just going to change that variable. So instead of having a z in place, I'll have something else there. If we're talking with the moment from the yz plane, x is what tells us that direction. So we're going to have x times the density. Which is still going to give us 7k over 12. And then the last one's the same way, only have y in place, but it equals the same constant. A lot of symmetry in this problem. So the actual final answer that we care about is going to go through and find the x bar, y bar, and z bar. So x bar is going to come from the moment about the yz plane. Y bar is going to come from the guy on the bottom we have here. And z bar is going to come from this one. But they're all the same, and we go through and divide those guys by k. We're just going to get the point 7/12, 7/12, 7/12. So I did not do like any of the math here to get that, but hopefully you can kind of follow if you go back over this one. All right. Questions or comments?
Oh, wow.
Again, I would really encourage you guys to make sure you're okay with setting these things up. I mean, I skipped a lot of the math here. On the test, I'm going to ask you to do that sometimes too. I'll expect you to go through some of the problems or part of the problems, but I really want to make sure you can set them up. Because if you can set them up, eventually you can fight the math. But if you can't set them up, it doesn't matter how good you are at the rest of it. It's just not going to work. You've got to understand the application piece. So hopefully it kind of makes sense where these parts come from. I didn't spend a whole lot of time on this as much as we did the other ones. But understanding where those limits of integration come from, you see that carries through in all these things here. And the next section is going to be there too. So you really have got to understand how this shape works, how this shape projects onto the XY plane and things like that. Next section, we'll go ahead and start. It's taking these same ideas and just saying, well, we mentioned that in some of these examples, polar coordinates would be a whole lot easier to go back and use. So let's do that. Let's talk about converting these triple integrals to different coordinate systems. We've got two different coordinate systems that we can convert to. If you recall way back in chapter 11, we talked about cylindrical coordinates, which are pretty much just polar coordinates and z. And we also talked about spherical coordinates, which were a lot different. Spherical coordinates had radius and then two different angles we were looking at there. And we'll get to that later on. We'll talk about the polar coordinate version first. Okay? And I will warn you, there are lots of times where I am going to say polar coordinates instead of cylindrical coordinates, and I apologize. They are technically cylindrical coordinates, but in my head, they're like the same thing. If I say polar, very often.
So, I'm seeing we have very few pages left to chapter 14. What is the plan?
The plan is the test for this will be a couple days later than what it says in the original thing. So chapter 14 test was supposed to be today. Yeah, that's not happening for sure. We will probably finish chapter 14. I was thinking about this earlier. Probably finish it like Tuesday, maybe Wednesday, probably Wednesday. So the end of next week will be the test over this stuff. If you want to put dates, let's say from the 7th, although I don't know if anyone's going to want to take it that early, 8th, 9th, and we'll leave it Sunday, maybe Monday if we need to. So end of next week.
I just noticed that.
No, yeah, we're very close to the end. Okay, here are the conversions that we had for working with polar or cylindrical coordinates to rectangular coordinates there. And we know these already. Okay, we've worked with polar coordinate stuff that we know this. You know, x equals r cosine theta, y equals r sine theta, and z is just z. Doesn't really change. And then the second version down here is just kind of sometimes helpful for shortcuts and converting these. When are polar coordinates handy to use? Like when we are working through a problem, what in that problem tells us to go back to polar coordinates? Curved surfaces, specifically like really circular surface here. So same thing's going to happen here. Cylindrical coordinates, which are just polar coordinates in 3D, they work really well when we have circular regions of integration. That part doesn't change. It's the same thing we thought about before for polar coordinates. However, now that we're working with triple integrals, we have the kind of like one more variable that we're going to see a lot of times here. Another times these could be handy is also when we have cylindrical surfaces. And we'll work through some examples, hopefully to kind of point out when that happens or not. But there's different cases where this occurs. And again, like before, what part of the thing is going to be isn't just going through and doing it, but recognizing when this is going to be a handy conversion to go back and do. So hopefully we can point that out. Order of integration, we've got a couple different options here. How do you go through and decide that? If you want to just kind of default to dz, dr, d theta, that would be a-okay. Kind of like before we said dr, d theta. I just had that third component there. But it could be any of the 6 different combinations of these. You could also do dr, d theta, dz, if that for some reason was easier. Or maybe you would do dz, d theta, dr. I mean, I'm not going to go through and write it, but there are 6 different things you can go through and do here that would work. And any of them are fine. So having a default just makes it easier to kind of start the problem, but know that you can definitely change order of integration. You don't have to stick with the z, dr, d theta. Depending on the shape you're working with, or when you're going to do that integral, if it's too difficult, we can go back and change this. Okay? And then limits of integration, we have the same ideas we had before. We want our innermost limits to be the most complicated and our outermost to be the simplest. So innermost limits are most complicated. And then the outermost should just be constants, but they should definitely be the simplest. We're going to see a lot of similarities between working with this and what we have with polar coordinates, so I hopefully don't have to explain a whole lot there. But there's our working with this. The triple integral is the first form of it. Technically, the second part is an iterated integral. We still have that conversion factor r here that hasn't changed. So really what this is saying is just make sure everything gets converted to r, theta, and z. You don't want to just pick the easy parts, but every single piece of your integral has to be converted to r and theta and z. All right, this is the one I was talking about. Okay, we're gonna set this guy up, and then we'll start working through and we'll kind of see how far we get. Find the volume of the solid, and we do need a lot of room here, so this page is not left blank on accident. Find the volume of the solid of region Q cut from the sphere with a radius of 2 by the cylinder of r equals 2 theta. Let's see if this will apply. Okay, so sphere radius 2. I hate that it doesn't just get out of that. Okay, so there's our sphere radius 2. And I did write it in rectangular coordinates just because it's easier to type it. The cylinder we're working with, won't do it. Polar coordinates. Oh, dang it. Okay, the cylinder that we are working with, it is a circle. I'll graph it over here because it's easier to graph that here, but this won't do 3 dimensions. So here's the circle that we're working with here. Imagine taking this circle and then just stretching it up, okay? We're just taking this whole thing and just making a cylinder out of this here. So use your imagination a little bit. If we think about graphing that circle, it's going to kind of sit right over here on that green axis. It's going to go from the origin all the way to the outside of the sphere, but it's just basically going to cut through it. So if you have this ball, this solid ball, and you were to drill a hole from the top down, it would go right along your z-axis, not past it, and it would touch this circle at the end right there. And that's kind of the little shape that we're talking about here. I didn't think about not being able to get that to graph on that program. If I try to sketch it over here, let's see how this turns out. So here's my sphere. There's the origin. So our cylinder is going to be a circle that sits right over here and then just goes straight up. Hopefully that's not too bad, but that makes a little bit of sense. So again, you have a ball and you like drill a hole down the side of it. It's kind of a weird thing to do. And what we want to find is that piece that we're making on the inside there. So it's kind of going to have a curved-ish top. That's not helping any. I'm not going to do that. But we're going to have that weird, I don't know how to even describe it, a cylinder with like a very rounded edge on the side of it there. Okay. And that's what we want to find the volume of. So let's get this guy set up here. We're already given this thing in polar coordinates, so we should keep it in polar coordinates. Another 2 big hints that polar coordinates are helpful is our region of integration is a circle within a circle, but we have a whole bunch of circles here. The cylinder we're talking about is a cylindrical surface, so all these things are good hints that cylindrical coordinates or polar coordinates are going to work out well for us. So if we go through and set this guy up, let's look at one more thing before we do this, the region of integration on the xy plane. So if you imagine looking at this picture from the top down, we have that sphere that has a radius of 2, and we've got that little circle on the inside that has a radius of 1, but that little circle on the inside. And the region we care about is going to come from right here. Okay, that's our region of integration, is inside this little circle. So it's really just that circle is all we care about. The fact that we have this sphere doesn't change anything for our region of integration. So set up limits, we'll leave a bit of space so we have room to go back and write. Volume is always going to have an integrand of 1, but since we're converting to polar coordinates, have to multiply by r. And then let's stick with dz, dr, d theta, and see if that's good enough. Okay? Okay, so limits for z. What is this solid bounded by on the top and the bottom?
Okay.
Yeah, to be more specific, the sphere, right, the sphere. So we've got the top part of the sphere over here is bound at the top, and the bottom part of the sphere over here is bound at the bottom of this. So if we take that sphere, which we still haven't written the equation for, let's go back and do that. Well, it's radius of 2, so 2 squared. We know we're not working rectangular coordinates, so let's go ahead and put this polar coordinates. X squared plus y squared equals r squared. So we've got r squared plus z squared equals 4. That would be the equation of my sphere in cylindrical coordinates. Solve it for z. Positive or negative, skip that. And that hopefully makes sense. The positive square root is the top part of this, and the negative square root is the bottom part of this. So those are going to be our limits of integration. Or negative square root of 4 minus r squared to a positive square root of 4 minus r squared. Okay, it's the top part of the sphere, bottom part of the sphere. And right now we're just saying the whole sphere is all those limits of integration are doing. When we go back and look at dr, we're going to kind of hone in on the specific section we need. So what are limits of integration for r? And now consider this. So we're thinking about dr and d theta. Think about this picture down here. So what are the limits of integration for r?
R is from
for the inner thing or the outer one.
Well, we want to know about, we don't really care about this. So I'm going to go ahead and erase this. That doesn't make a difference. This little gray circle is really all we care about. Because we're making our cut, that's the only place we're going to keep.
Does the origin matter?
The origin does matter because the smallest r is going to get is 0. This thing does touch the origin. So our lower bound for r is going to be 0.
Yeah.
Okay, because we go right down to the origin there. Is it going to be a constant? Let's just go with that. Is it going to be a constant for our upper limit? Is the radius always the same everywhere on this graph? Remember, radius is talking about this distance here. Is that the same for any angle we go to? Are all those little pink lines the same length?
Oh, it's saying
Yeah.
What is r?
it's y equals 2 sin theta.
Exactly. R equals 2 sine theta. Okay, that function is what our r is ranging from. It goes from 0, and then just depending on what your theta value is, so 2 times sine theta, depending on what your theta value is, that tells you how large your radius you are. So yeah, that little gray circle has a radius of 1, but we don't care about that. We have to remember that r is talking about from the origin out, what is the radius of this region. It is not always the same. For different angles, this region has a different distance, and that's why we're going to put the function in there for. Okay, so limits of integration go from 0 to that cylinder, to 2 sine of theta. Okay, how about limits of integration for theta?
0 to 2 pi.
Not even 2 pi.
Pi?
Yep, we can just go to pi, and that's good enough because we don't have anything on the bottom. Okay,
Okay,
so we might as well just stop.
I don't know if it was like
Wait, what
2
is
pi because it does make the complete revolution or what to do.
I would say if there's nothing there, just stop. We're just going to kind of go where the curve actually is. I mean, it's, yeah, I won't show you other pictures there. No, we're not going to go the whole revolution. We're just going to go from there.
Would the whole revolution be like a figure 8?
No, because this is the whole thing. If you graph sine of, or 2 sine of theta, it is just that little gray circle that is in there. Like, think back to this. When I graphed it here in Desmos, I mean, that is it. There's no other places to this.
Oh, no, I get it. Because
So,
no, that is so.
If we went, okay, and here's the problem I have with this one, okay? The way the book goes through and finishes solving this is it says, well, instead of solving this integral, we're going to say this thing is symmetric, right? We have this symmetric sphere, the symmetric cylinder. They cut it in half, and they're just going to go from 0 to pi over 2. And they're just going to look at this little portion right here and double it. So all the other integrals are the same. Squared r p c c r d theta. And then the book goes through and solves this, which makes sense because we've got a symmetric shape here. We're splitting this thing in half. Now we're just thinking about going from 0 to pi over 2, so just talking about this part of it. So yes, we've got to go through and double it. But this kind of relates back to the question you asked there too. When I solve the problem this way, it's fine. I get the same answer as above. When I solve the problem without doing that split, I get a different answer. I cannot figure out why. And that's the part I talked to Mr. Boateng about too. I'm guessing it has to go with the thing you're talking about there is, if we think about this thing as whole thing from 0 to 2 pi, we're accounting for a lot of stuff in the bottom that isn't really there because there's nothing there.
Right.
And that, I don't know. I just don't know. And I was really hoping I'd have an answer before class for it, but I don't. So we're not going to be able to finish this. We're running out of time here. But if you go through and finish solving this inequality, this equation here, you end up getting some weird fraction. I'll give it to you guys on Monday. But it's a different answer than the first one. So here's what I'm going to ask you guys to do if you're bored and want something to think about. If you can figure out why we get different answers, let me know. That's going to be my task for the weekend too. Otherwise, when we come back on Monday, we are definitely going to go back and solve it this way since that's what the book does. But I really need to know why they're different there. And I'll also think about your 2 pi thing because I don't have a good answer for that. I don't know. So anyway, I'm very confident that this initial setup is okay. I know that is not wrong. There's just something weird about the math that kind of changes in the middle. I can't figure it out. So when you're working on your homework, this stuff won't be there. The polar coordinates right to the spherical coordinate stuff isn't on there. But if you do have questions over 4.6, if you just finished up today, let me know. And I'm okay doing something about that next week if needed. Okay, you're thinking, Russell, what are you going to say?
We're just looking because you say I have to double it. And just...
Oh,
Okay, now I see where I have to double.
Yeah, because they're just taking like going halfway around instead of all the way around, so they're doubling it, which I get and it makes sense. I just don't know why I get different answers. Those are equivalent integrals. Why on earth did they give me different answers when I solve it? It's annoying too because I can't come up with an answer. Like one of those things where there's probably just some simple little thing that I'm just overlooking, but I don't know. So anyway, you're leaving your teacher on a note of confusion until Monday. And then just that's it. That's all. So don't ask me questions about this one because I can't answer them yet, but I will be able to answer them on Monday. I'll get things figured out. Okay. Like I said though, homework 4.6, the stuff won't show up there, and then we'll take care of the rest of it next week.
yeah, this one is right.